Bismillah ar-Rahman ar-Rahim. The topic of today is water dissociation. Water dissociation is a very important topic because when we talk about ABG or arterial ballot gases, we are talking about a certain compartment which is the extracellular compartment, which is formed of the plasma or the blood and the interstitial fluid. This compartment is formed mainly of water as the solvent. Dissolved in it carbon dioxide, protein, inorganic and organic substances, in addition to oxygen and nitrogen. What about this water? This is a big solvent. It is very important to know that this water, if you consider it 1000 ml of water with a density of 1 gram per milli, this will give you 1 liter of water will give us a weight of 1 kilogram. If the molecular weight of water is 18, this means that 1 liter divided by 18 will give you 55 by 0.5 moles. So 1 liter of water will contain 55.5 moles. So the molarity of water is 55.5 moles, not millimoles. It's moles. It is very large, and this volume is constant. When you come to the dissociation of water, part of this water, H2O, dissociates into hydrogen ion and hydroxyl group, hydroxyl ions, hydrogen cation and hydroxyl anion. How much of this 55.5 moles dissociates to give us this anion and cations? So this is what we call dissociation constant, which is about 1.8 multiplied by 10 raised to the power minus 16. At what temperature? At room temperature, which is the 25 degrees centigrade. At other temperatures, it is different. That's why you call it constant. So the dissociation of water will be this value and will never change from this value so long as the temperature is 25. We'll come back to this very important point. Water dissociates at room temperature 25 degrees centigrade into hydronium or hydrogen ion, simply to simplify matter, and the hydroxyl group. If you have this dissociation constant we mentioned before, multiplied by this water, this multiplied by this large volume of water, 55.5 mole, it will give us how much of this water dissociates to hydronium or hydrogen ion and hydroxyl group. If we multiply this, since this is a large and constant, and this constant, this will give us another constant, which is dissociation constant, new one, will give us hydrogen ion and hydrogen cation and hydroxyl anion. This dissociation constant, if we multiply it, 1.8 multiplied by 10 raised to the power minus 16 multiplied by 55.5 mole, it will give us this value. It will give us 1 multiplied by the 10 raised to the power minus 14. This number equals the hydrogen and hydroxyl. And since the dissociation percent, this is 0.5, 1 and 1 to 1, so this will have half this value will be for hydrogen and the second half for hydroxyl group. So the hydrogen ion concentrations will be 1 multiplied by 10 raised to the power minus 7, and the same for hydroxyl anion. It means that we are dealing with this dissociation constant minus 14 equals hydrogen and hydroxyl. If we take the power of this dissociation constant, the pk, this is a negative logarithm of that. So the pk of this dissociation constant, if you take it, this is a negative logarithm, will give us pk will be 14. This means that the pk of water, the power of dissociation constant of water, which is 14, equals the power of hydrogen plus the power of hydroxyl anion. Since the two, this is the ratio between the two, 1 to 1, this means that the power of hydrogen will be 7 and the power of hydroxyl group will be 7. This is very important to notice, because this is this dissociation constant, or this dissociation of water at room temperature at 25 degrees centigrade. So at room temperature, this is the concentration of hydrogen ion, and this is the power of the hydrogen ion, which is equal to the concentration of hydroxyl group and the power of hydroxyl group. That's why when you look at the pH of water is 7 and BOH of water is 7. If this pH changed, instead of being 7 to become 6 or 5 or 4, this means that is some sort of acidosis, because this means that there's an increase in the hydrogen ion. Decrease in the minus, this means increase in the hydrogen ion. The reverse is true when the pH is 8 or 9 or 10. This means that there is increase in the negative. This is mean that there is decrease in the hydrogen ion. And so this is alkalosis. So in these directions alkalosis, in these directions is acidosis. Again, back again to the dissociation constant of water. We have mentioned that at 25 degrees centigrade it is 14. This is at room temperature. This means that any change of hydrogen or hydroxyl group, the summation of the two will be 14, whatever you add. If I added an acid, this hydrogen ion will increase. Concomitantly, the hydroxyl group will decrease, and if you add the two together, the summation will be 14. That's why we called it dissociation constant. It is constant at that degree whatever you add, hydrogen or hydroxyl group. Finally, if a hydrogen has been added, hydroxyl group will decrease and the two will be 14. The reverse is true. The same thing if you take the dissociation constant of boiling water at 100 degrees centigrade. Dissociations will increase. Instead of being minus 14, it will be minus 12, and the pK will be 12. So the pH of water at 100 degrees centigrade will be 6, and the BOH will be 6. If you add something or like that, hydrogen or hydroxyl group, the two together should be 12. So this is a very important point when we talk about the dissociation constant, because this will serve us and help us to understand what is the pH of neutrality, which is important for the maintenance of the ionizations of the cell. Constant of the ionization of the cell should never change with the change of the temperature, because the change of the temperature will be associated with the change in the pH, and the pH is the pH of neutrality at each temperature. Look back again, this is water. The pK of water equals 14, pH is 7, and BOH is 7. If we add an acid, this like HCl, this means that you are adding a hydrogen ion. So the hydrogen ion will increase, and concomitantly the hydroxyl group will decrease in order to give us a pK of 14. Imagine if you say that we are adding some ions or some cations like HCl, hydrogen cation has been added. This addition, this means that there should we imagine as if there is some sort of decrease in the dissociation of water. Instead of being minus 14, it will be minus 15, and the hydrogen ion will be minus 7.5, and the hydroxyl group will be minus 7.5, each of them. Addition of hydrogen ion will increase the concentration of hydrogen ion, and instead of being minus 7.5, it will be minus 6.5. And in this case, the two together should be 14. This means that if you take the pH of minus 6.5 will be 6.5, and the pOH will be 7.5. Or in another way, if there is some sort of increase in the hydrogen ion, this means that there is a decrease of the pH, and the pH plus the pOH should be 14. Although we have added something, this because the water, the mole of water is very large, 55.5, and dissociation of water is very small, so it can react with anything to be added with it without any problem. And so the percent of dissociations of water at that temperature will never change. Look, if we look at ammonium chloride, if ammonium chloride is dissolved in water, what is the pH of this ammonium chloride? Ammonium chloride will be dissociated into chloride and ammonium will react with water or dissociate in water to give us ammonia and hydrogen ion or hydronium. This means that there is an increase in the hydrogen ion. Increase in the hydrogen ion, this means that the pH will be less than 7. Concomitantly, there is a decrease in the hydroxyl group, and the hydroxyl group, the pH will be more, the pOH will be more than 7. So simply, this is ammonium chloride is an acidic because there is increase in the hydrogen ion, and this hydrogen ion will be associated with decrease in the pH of water. Instead of being 7, it will be less than 7. Before we go, when we talk about this dissociation of water, I think we have to take just a rapid look about strong ion difference. We are going to talk about it separately. Strong ion differences, this means that when we look at the cations and the anions, all of them, there is the cations equals the anions. This is an electroneutrality. So there should, when you look at sodium plus potassium plus calcium plus magnesium, so equals these anions: chloride, bicarbonate, total weak acids, lactic acids, keto acids, all of them. But usually when we measure these strong ions differences, which is sodium plus potassium plus calcium plus magnesium minus the strong anion, which is chloride. This equals 40. What's meant by 40? This equals the bicarbonate and the total weak acid. Total weak acid forms about 16 milliequivalent, and bicarbonate 24, and all of them, they will be 40. In another way, this bicarbonate, sodium bicarbonate, when dissociates in water, it gives you carbonic acid, which does not dissociate, and the hydroxide group. So when we talk about the strong ion difference, sodium minus chloride equals 40 hydroxyl group. Right, so this is a very important point. Look at it. So when we come to the water, strong ion differences is less than 40. Less than 40, this means that the hydroxyl group is less than 40. So the hydroxyl group, there is a decrease in the hydroxyl group, there is a concomitant increase in the hydrogen ion. So this means that it's acidosis, and the pH in this case will be less than 6. So this is when we look at the problem, this is a dissociation of water. Strong ion difference is less than 40. This means that the hydroxyl group is less than 40. There should be a concomitant increase in the hydrogen ion. We measure the hydrogen ion, and so we measure the pH, not the pOH. The pH in this case will be decreased, and so there will be some sort of acidosis. The same thing if you add sodium hydroxide. Sodium hydroxide is dissociates into sodium and hydroxide group, and the hydroxide anion This means that there is increase in the hydroxyl. Increase in the hydroxyl group, there will be concomitant decrease in the hydrogen ion. Decrease in the hydrogen ion, this means increase in the pH. So this is some sort of alkalosis. Same thing. So this is another. This is a problem of water dissociation. So addition of acid or addition of alkali. This means that the change is the percent between the hydrogen and hydroxyl ions of water. So it is the pH of water, not the pH of the material added. The same thing if you look at sodium acetate, sodium lactate, sodium bicarbonate, all of them dissociates and finally they give us a hydroxyl group. Sodium acetate dissociates into sodium and acetate. And acetate dissociates in water into acetic acid, which is non-dissociable. So the hydrogen ion is not due to acetic acid, but the hydroxyl group is responsible for the productions of alkalosis. So in this case, the hydroxyl group will increase. Increase in the hydroxyl group will be associated with concomitant decrease in the hydrogen ion, so the pH in this case will be larger than 7. So there will be some sort of alkalosis. This is very simple way. The same thing you can look at it. Strong ion difference, which is the difference between sodium and chloride. If it is more than 40, this means that we are dealing with increase in the bicarbonate or increase in the hydroxyl group. Increase in the hydroxyl group concomitantly will be associated with decrease in the hydrogen ion. Decrease in the hydrogen ion, this means this increase in the pH. And so this is an alkalosis because this plus that should equal the pK14. Increase in the OH will be associated with decrease in the hydrogen ion in order to give us finally pK14. So this is a pK14. To sum up, this is if you look at the pH of water is 7.4. This is mean that the hydroxyl group is a little bit more than the hydrogen ion, and the two together are 14 at this temperature. This shows the strong ion difference is 40. If you look at these strong ion differences more than 40, usually it is common. This is in the problem of alkalosis. This means that the hydroxyl group will be more than 40, and this is the hydroxyl group. So this is, and at the same time there will be concomitant decrease in the hydrogen ion. The two together will be 14. This is what happens in the case of a patient who is having vomiting. This will result into hypochloremic metabolic alkalosis. Hypochloremic metabolic alkalosis, loss of chloride, concomitant increase in the bicarbonate, and this means the concomitant increase and the hydroxyl group. This is one point. Another point you can look at strong ion differences with with increase in more than 40. But this is not due to vomiting, as I mentioned, but due to addition, say, sodium acetate. Sodium will increase for sure. At the same time, the acetate will dissociate and to give out the hydroxyl group. So the hydroxyl group increase, concomitant decrease in the hydrogen ion. So this also will give us a strong ion difference more than 40. This is a sort of alkalosis. More than 40, hydroxyl group increase, hydrogen ion decrease. Strong ion difference is less than 40. This means that the hydroxyl group is decrease. Concomitant increase will be associated with the hydrogen ion. So this is a sort of acidosis. Like the same thing if the patient is having diarrhea. There is a loss of bicarbonate and concomitant increase of chloride. Loss of bicarbonate, this means loss of hydroxyl group. Concomitantly, there is an increase in the hydrogen ion from water. So this is a case of metabolic acidosis. This is this is a rapid look at the dissociation of water and its relation with the strong ion difference and its relations with the dissociations of salt in it. And so to conclude, also this is the hydrogen ion or hydroxyl group, which determine the pH usually are that of water, not of the substance added to it. So the dissociation of water is very important to look at it when we look at the pH, change in the pH regarding to the salt added or anything added to it. Thank you.